Step into a forest on a warm summer night, and you might find yourself surrounded by thousands of tiny, glowing orbs. It appears as a silent symphony of light, painting the darkness. When viewed through the lens of human engineering, this woodland scene presents a physical paradox. For most of our history, the rule for creating light was simple. You had to make something incredibly hot. Think about a traditional incandescent bulb. If you grab the glass while it's turned on, you're going to burn your hand. About 90% of the energy going into that bulb is wasted as pure heat, with visible light acting as a minor byproduct. We've certainly improved over the decades. Modern LEDs run much cooler and waste far less energy, but even they require heat sinks to manage their thermal output. Designing a bright light that generates no heat is a massive engineering challenge, which brings us back to the firefly. If producing illumination is inherently tied to generating heat, the tiny insect should cook itself from the inside out every time it flashes. The answer lies in biochemistry. Millions of years before we ever wired a circuit, biological evolution bypassed the heat problem entirely, mastering the exact recipe for cold light. To see how they do it, we have to look inside. The bottom section of a firefly's abdomen houses a specialized organ called the lantern, an organic reaction chamber. Inside the chamber, the insect produces a complex molecule called luciferin, the biological fuel. It then introduces an enzyme catalyst, luciferase, which binds to the luciferin. Finally, a pulse of ATP energy is injected, charging the locked molecules for action. At this point, the lantern is fully loaded. It has the fuel, the catalyst, and the power. Yet, the chamber remains completely dark. The factory is built, but it waits for the insect to throw the final switch. Insects don't breathe with lungs. Instead, the firefly relies on a series of muscular valves that connect directly to the outside air. When ready to shine, it flexes these muscles, snapping the valves open and sending a rush of oxygen straight into the lantern organ. That oxygen is the trigger. As the gas floods the chamber, it slams into the energized mixture of luciferin, luciferase, and ATP. The collision creates intense bioluminescence. Nearly 100% of the energy emits as pure light, with almost zero thermal waste. There are no glowing hot filaments or bulky heat sinks, just perfectly calibrated chemistry executing an incredibly efficient reaction. Because the entire process relies on mechanically controlled breathing valves, the firefly has total command over its illumination. It can cut off the oxygen flow just as quickly as it started, allowing it to blink its cold light on and off at will. This ability evolved into a highly precise biological Morse code. Depending on the species, the timing and pattern of those flashes tell predators that the insect is toxic, while simultaneously signaling to potential mates hiding in the grass. The efficiency of this natural system is so reliable that human scientists now artificially synthesize the firefly's luciferase enzyme. We use it to monitor cellular growth and detect the progression of diseases in medical research, relying on that exact same chemical glow. When you see a forest illuminated by yellow-green streaks on a midsummer evening, you are looking at the visible signature of a sophisticated chemical process. These blinking lights represent millions of perfectly engineered, highly efficient biochemical factories, communicating in a language of light.